Welcome back to Seacoast's remote trigonometry class. My name is Eric Fearing. I use he, him pronouns, and most of my students just call me Mr. This is part 2 of Competency 3, Benchmark 1. This part of the benchmark is about how the unit circle provides us answers for trigonometric ratios of angles greater than 90 degrees. I alluded to this in my previous video when thinking about how we could find the x and y coordinates of a 0 degree straight out to the right point on the x-axis or a 90 degree straight up point on the y-axis. But at that time we just looked at things in quadrant 1 where we can draw a triangle with an angle from the origin of 30, 45, or 60 degrees. We could draw a triangle of any size angle at the origin there. And then we're just going to have positive answers for all of our side lengths, which makes sense. If we look at things that go over to the other quadrant, we can continue to give answers based on the x and y values, but we're going to get some funny things because the x values in quadrant 2 are negative. Negative x's, positive y's. So in a triangle, you could never have the ratio of the adjacent to the hypotenuse as a negative number because we don't actually have negative measurements. But when we think about how far to the left and right things are as we go around a circle, we can use that definition based on the unit circle to get answers that are negative because we can't have things like a 110 degree angle in a right triangle. So to explain this a little more, I've got some color-coded what are called reference angles, are familiar ones from the previous video. 30 degrees, 45 degrees, and 60 degrees. If we counted up by 30 degrees from 0, we'd be at 0, then at 30, then at 60, then at 90. If we went up another 30 degrees, we'd be 30 degrees over to the left. We can imagine a triangle that is a 30, 60, 90 triangle pointed that way. And now its base would be a half long and its height would be root 3 over 2 if the radius were 1, the hypotenuse were 1. So we can know for sure that the coordinates of this point at the 120 degree angle would be negative 1/2. The length along the bottom, the short leg, would be to the left. So negative 1/2, and the y value would be root 3 over 2. So we could say that the cosine of 120 degrees, according to the x is cosine because it's the adjacent leg in quadrant 1, it's not really the adjacent leg anymore because the triangle's not so perfect. It would have the same length as that 1/2, but the cosine of 120 degrees would be negative 1 over 2. Similarly, the sine of 120 degrees would be positive root 3 over 2. These are the same absolute values as the 60 degree mark. And because they share the same height and they're a reflection of each other over the y-axis. We would say 60 degrees is the reference angle for 120 degrees because it's got the same x and y coordinate absolute values, just the signs are different. There are two other places around the unit circle that are in that same situation. We reflected over the y-axis to get 120 degrees. We could also reflect over the x-axis to find two more places that are 30 degrees away from the y-axis, but on the negative side of the y-axis, so almost straight down. If we counted our way around the circle, we'd have 0 degrees, 30 degrees, 60 degrees, 90, 120, 150, 180 would be straight across, 210, and then 240 degrees would be there. 270 degrees is straight down, and then 300 degrees would be here. Now in quadrant 3, we have both negative x's and negative y's, and in quadrant 4, we're back to having positive x's, but we have negative y's. So these are going to have the same absolute coordinates, but negative 1/2, negative root 3 over 2, and here positive 1/2, negative root 3 over 2. So all four combinations of possible positives and negatives on those two numbers create these spots that are reflections of each other as we go around. We can do this same sort of counting off and find things that have a reference angle of 30 degrees. 30 goes around and it's 30 degrees up from the x-axis. 30 degrees up from the x-axis here would be a 150-degree turn. Not all the way to 180 yet. And that would have coordinates of negative root 3 over 2, 1/2. Then just after 180 degrees, we'd be 30 degrees down, 210 degrees, where we have negative root 3 over 2, negative 1/2. And then 30 degrees away from completing the circle would be 330 degrees. So all those light green ones are also going to be reflections of each other with the same absolute coordinates. And now the 45-degree ones, we could be right in the middle of each of the four quadrants. And all of those are going to have the same root 2 over 2 absolute value, but here the x will be negative root 2 over 2, so the cosine is negative. The sine is positive because the y is positive root 2 over 2. How high up is it? How far to the right is it? A negative amount. It's to the left. Here, where we're down and left, we're going to get negative root 2 over 2 and negative root 2 over 2. Similarly, we'll have positive root 2 over 2, negative root 2 over 2 there. This is going to be quite a mess. 45 degrees more than 90 is 135 degrees, which is 45 less than 180. 180 plus 45 is 225 degrees. I just want to get a little bit more red ink on here so you see all four of them. 270 degrees is straight down. I might as well label that. You're going to want to see it. 180 degrees. And then our last angle to label here. 270 plus 45 is 315, which is 45 less than 360 degrees, which is the same thing as 0 degrees. And that's important because we could certainly take the measurement of a larger angle, like a 360-degree angle would come up the same as 0 degrees. Cosine of 1, sine of 0. If we did 390, we'd go 360 the whole way around, plus another 30. So 30 plus 360 is 390. It would be the same sine and cosine as 30 degrees. And that lets us use trigonometry to map processes that go around and repeat. We call them periodic, which is the topic for competency 4. So I want to show you a filled out graphic of some of this stuff. So here are all of those angles. And this doesn't include the sine and cosine values. There will be a post like that on the website to help do some of the reference work. But this one's nice and clean and shows the important degree measurements in a slightly more precise way than my sort of eyeballing it. You might want to think about how these would be color-coded. 30 is related to 150, 210, and 330. Those all have that same reference angle. And if we added or subtracted 360 degrees from any of them, we'd end up still at that same reference angle. So they're going to have the same x and y absolute values. So in the problem set, you're going to answer questions like find the reference angle for 213 degrees. Okay, 213 is not on the unit circle diagram we have because it's not one of those common 30, 45, or 60 degree angles. But we can tell it's in quadrant 3. Okay, so it's more than 180 degrees, it's less than 270 degrees. The question is, okay, if it were reflected over here, right, there's going to be 4 spots that have those same reference angles. We want to know what angle this would be if it were turned in quadrant 1 with those same coordinates. I want to think about how far it is from one of the axes. So this is 180 degrees right on the negative x-axis. 180 plus 33 degrees would get me 210. So it's almost a 30-degree reference angle, but it's 33 degrees down. That means it would align with things that were 33 degrees down or 33 degrees up, which means our answer is in fact 33 degrees because it would come up 33 degrees there. This would be the same answer as if we took 360 and subtracted 33 degrees. That would give us 360 take away 30 is 330, must be 327 degrees. Would also have a reference angle of 33. We would have thought 360 minus 327 gives us 33, so it goes up 33. And here in quadrant 2, 33 degrees before 180, 180 minus 33, 150, 147 degrees. So find the reference angle for 213 degrees. It's 33 degrees because it's 33 degrees from the x-axis. Now we can take that one step further and be asked about the sine or cosine of an angle that's not in quadrant 1. Here you're going to need to look back at your sine and cosine values we talked about in part 1. First, we'll want to find a reference angle. 210 I picked on purpose because it's very close to 213. I'm confident that this is 30 degrees more than 180, which means it's going to have a reference angle of 30 degrees more than 0. So the cosine of 210 degrees is going to equal the cosine of 30 degrees. And you can go back to a reference sheet and say, okay, the cosine of 30 degrees is the square root of 3 over 2. It's pretty far to the right because it's a shallow angle. So there you have it. This was about explaining how the unit circle coordinates could give us trigonometric values for angles greater than 90 degrees. You learned 2 skills, one of them finding a reference angle, and the other one an expansion on using x and y coordinates. Oh, I'm just realizing that I made a mistake on that last problem. You're probably all confused. So the cosine of 30 degrees is the square root of 3 over 2, but the cosine of 210 degrees doesn't quite equal the cosine of 30 degrees because the cosine of 30 degrees is positive and the cosine of 210 would have to be negative. Should be thinking about that. So the cosine here is negative and the sine is negative because quadrant 3 has only negative sine coordinates. So let's say the cosine of 210 is the opposite of the cosine of 30 degrees. My mistake. Happens to the best of us. Again, thank you for working on these 2 skills, and I look forward to getting your problem set.